Hello, and welcome to the pre-lab for Module 2. We're going to look at the Green River from two perspectives in this lab, this amended lab. This would have been 2 weeks of laboratory during the good old days, but we're going to do it all in one process, one video series that you'll have access to on Thursday. And it will be on two ideas, conductivity and on pH. And we're going to look at two things. How many charged particles? What's the concentration of charged particles in the Green River? And what's the pH? And I'm actually going to make two videos so that this is not too long and boring. I'll make two videos for you, one on conductivity, this one, and then one subsequently on pH. So first business, on Thursday, what you have to do is that module one report on TSS and turbidity graphs, a 3-paragraph conclusion. Any questions you have about that, make sure you write to me and ask me, and I'll hopefully be able to solve that for you. We also have a fairly engaging and long series of pre-lab assignments for Module 2. Basically, the pre-lab that would have been done due for the first week in the good old days, and the pre-lab that would have been done due for the second week, one on conductivity, one on pH. They'll both be due. So that is 43 through 47 for conductivity, and then 57 through 61 in the lab manual for pH. And so let's talk about conductivity first. Now, conductivity's got an interesting unit. It's actually in units of microsiemens. So that funny little u, it's actually a Greek small m, microsiemens. It's actually the reciprocal, logically, the reciprocal of resistance. You've probably done V equals IR, and R is resistance in a wire. This is the reciprocal. As resistance goes up, conductivity goes down. This is the reciprocal of resistance. And so it's in microsiemens, SIEMAN, the same guy who invented Siemens, the company that make all kinds of analytic equipment. So we're really going in this pre-lab to talk about two theories, two ideas that will make you able to do the pre-lab and understand the videos better. And the first is about concentration and the units of concentration. It's likely you've heard this before in another course in high school chemistry, or maybe in 113 already. But that unit is molarity. And molarity is one of the units you could pick out. You could have done grams per milliliter. We saw that last module. But this is a conventional unit that uses moles. Moles is a unit where, the mass of carbon is 12 grams. So let's call 12 grams 1 unit of carbon. And you'll probably have heard this already in lecture. If not, you will soon. So it's the number of particles, the amount of moles in a liter. It's concentration. It's no more or less than a description of how salty a water is. How many moles, instead of grams, how many moles of salt are in a conventional liter? And so to talk about this and to talk about equation writing, I'm going to switch over to my new toy. The first idea is going to be about concentration, right? And concentration, and I have to write with a funny hand up thing, so I apologize in advance for my handwriting. That's the capital M is molarity. And molarity, as we said, how much salt in moles? We'll say moles of solute per liter of solvent. And that's the conventional unit of concentration. The thing about concentration to keep in mind is if I have something that is 1 mole, let's say it's 1 mole of salt, which is 58 grams, in 1 liter, 1 molarity, or we say molar. That concentration is constant. If you have a pitcher of 1 molar salt, there's my high resolution pitcher, and I pour it into all these cups of solution, assuming it's homogeneous, which we're going to assume for this lab, all of these also are 1 molar, right? So, the volume is not important. It's the amount of stuff per volume. So you're going to see a whole lot of solutions. We'll mostly be doing them in pretty dilute concentrations, not at 1 molar, but at like 0.1 molar, or, you know, right, something like 100 millimolar or 25 or 20 millimolar. And this is how scientists do concentration. We do it in terms of molar. The first thing that you're going to experience is we're going to take one of the one of the things we think might be running off from the housing estate, which is, so the concern here is that, and I think it's mostly the housing estate, that ionic materials, or this is largely about ionic materials, are dissolving in rainwater and leaching into the river from the over fertilization. And so we have a bunch of things that people put in fertilizer, like ammonium nitrate, that's supposed to be an NH4, and calcium and magnesium and iron, usually is +3, I think. All these things that allow plants to grow. We have a raft of potential ionic materials that could be put in. The first thing we're going to do is take ammonium nitrate, the top one there, and we're going to do a series of dilutions and see how conductivity is affected by it. And as you probably suspect, as the amount of particles goes down, the conductivity goes down relative to the number of particles. And be aware, this has 2 particles. Ammonium and nitrate. And this actually has 3 particles. 1 calcium cation and 2 chloride anions. We're looking at absolute number of particles. It doesn't actually matter what the particles are in terms of conductivity. What matters is how many. When you're talking about that, it doesn't matter what, it just matters how many. Here's a great vocab word that I'm probably misspelling. It's a colligative property, right? So if you throw salt in water, it raises the boiling point and the melting point, lowers the melting point, right? So that's why we put it on sidewalks. That's why you put it in boiling water with your pasta. It raises the boiling point. It cooks the pasta at a hotter temperature. Anyway, a colligative property. So we're going to do a series of dilutions, and I want you to understand the mathematics of doing dilutions. Here's the big idea, and it's kind of a cool idea. So let's say you have a large amount of ammonium nitrate at 100 millimolar, but you want 25 millimolar, right? So you're going to pour water in to dilute it, right? Just like if you had concentrated orange juice, you want it diluted so you can enjoy it, you pour water in. And what's true is that the number of particles, here come my particles, when you pour the water in, doesn't change. So the moles exist in here, and the moles at the end will be the same. Moles initial and moles final won't change. Okay, so if the moles don't change, we can do some simple math. We can look back at this relationship and we could say, well, if moles don't change, then the molarity, the concentration times the volume, right? We'll say liters. At the beginning, in this 100 millimolar solution, is going to be equal to the molarity times the liters at the end. In other words, if you have a certain amount of liquid at a certain concentration, if the volume goes up, the concentration goes down. It's kind of intuitive. And in fact, it's not just relatively true, it's absolutely true. It's an equation you can use. So let's say we're going to make 25 millimolar solution from this 100 millimolar solution. Well, we know that the initial concentration was 100 millimolar. Sorry about my handwriting. We want to know how much volume of that 100 millimolar we need if we're going to make 25 millimolar, and arbitrarily, let's say we want to make 200 mils of that. I know it's liters, but as long as I use liters and liters or mils and mils, they cancel. So how much of this concentrated stuff do I need? Well, let's say 25 times 200 all over 100. Just multiply both sides by 1 over 100. And I got 50 mils of that concentrated solution. But I need to have a total volume of 250, so I'll add 150 mils of water. And that sort of checks out mentally, right? So if I want to go from 100 to 25, that's 1/4 is concentrated. So I need to dilute it by 1 to 4. There it is happening. So that's a dilution. So let's do it another way. Let's do it in green, a different green. Let's say I have 25 millimolar, and I'm going to do a series of dilutions, 20 millimolar, 15, or maybe it's 16 and 12 and 8. And I don't know what exactly the dilutions are. Let's take that 25 millimolar and make 20 millimolar. So I start with 25 millimolar solution. I'm going to add some amount of that to a graduated cylinder because I want to make 20 millimolar at, let's say it's a small graduated cylinder, 10 mils. So I'm going to have a total of 10 mils. You can make any amount in the video. Who knows what they're going to make? I know, but you'll have to watch. So 20 times 10 all over 25. And that means 8 mils of 25 millimolar plus 2 mils of distilled water is 10 mils at 20 millimolar. So that's how you do dilutions. And you'll do a series of those. And then you'll have this graph where you'll have 0, 5, 10, 15, 20, 25 millimolar. And don't forget units, right? Concentration in units of millimolar. And you'll have absorbance. Absorbance, interestingly, has no units. So there'll be that, and you'll analyze 5. You can even say 0, 0 is a 0.5, and 10, and 15, and 20. And you'll add a trend line and be able to find a slope in an R-squared term. The Excel program will do that for you. And that's really how you do concentrations. And so we'll do that as an exercise before we look at the conductivity in the Green River. And so in the Green River, you'll end up conductivity in microsiemens per cm. And you'll have Green River sample sites. 1, 2, 3, 4, 5. And remember that at 2 is the housing project. So after 2, they collected water after the second site, site A, if you will. And site 4 is the textile mill, site B. And site 5 is the basin where the fish are dead. And we imagine, I'm making this up as I go along, that the housing project is totally responsible. And the thing about that conductivity in these particles is if you add it, they don't go away, right? So you don't imagine that it would diminish, right? As you go downstream, it would be the same. Maybe there's some charged particles from the mill. Like I imagined there could be some acid, right? And an acid, or at least for now, our definition of acid is protons. H plus is protons. I'll make a whole video on that. And maybe that causes it to go up, and you have a lot of charged particles in the river. And anyway, you'll find out what that bar graph looks like by watching the video, taking notes as you watch the video on conductivity, and examining the 5 Green River sample sites by this bar graph. I haven't found the greatest. The problem with freshwater fish is anytime you search for anything on freshwater fish, all you find is aquarium information. I think I found that a healthy range for freshwater fish is something like 150 to 1,000 microsiemens per cm. We'll see where that goes. And when you write this overall conclusion at the end of this, you'll talk about whether it rises in the 3rd paragraph, whether it is by itself criminal, the amount of charged particles. That's supposed to be an H plus proton. So that's conductivity. Let me mention one more thing because it's in the pre-lab and it's in the report, and that is about equation writing. So let me give you a molecular equation. You should do this in a new color so it's all explicit. The molecular equation, let's say I take calcium chloride, and I have sodium carbonate. By the way, states matter. Both of these are in solution. They're aqueous, meaning when you put these polar ionic materials in water, they dissolve. And when they are mixed together, these two dissolved ionic materials, you get two NaCl's, aqueous, but calcium and carbonate are insoluble. Solid. All right, so what's the ionic equation? The ionic equation is totally annoying because it's going to take a while to write. Patience with me here. Ca2 plus aqueous plus 2Cl minus aqueous plus 2Na. You can see this is totally annoying. Aqueous plus CO3, 2 minus aqueous. This is the equation of all the ions. 2Na plus aqueous plus 2Cl minus aqueous plus CO3, CO3, solid. Now, there's the totally annoying ionic equation. And yeah, no one wants to write that. And it doesn't really matter. A lot of what's going on in that equation doesn't matter, right? So for instance, you have NAs at the beginning, you have NAs at the end. You have chlorides and you have chlorides. These guys don't change. They're what they're formally called as spectator ions. What we care about is those particles that undergo change. So we can have a net ionic equation. Meaning what actually happened when I poured these two ionic materials together. What actually happened was the calcium particles came in contact with the carbonate particles. Whoops, sorry, that's an arrow, not a plus. And there's a net ionic equation. You'll be confronted with a bunch of those. I think there's a tricky one where they actually have H2CO3. And that's a weak acid, meaning it largely stays together. So be aware of that. And I think that in terms of the conductivity topics, that's really what you need to know to do the first half of this upcoming module, this experiment on conductivity in the Green River. So we're going to look at some standards first, and then we'll look at the Green River. And so that's the conductivity part. And hopefully this will get you through this little talk. Will give you what you need to do pages 43 through 47 in the lab manual, due on Thursday. Be aware. So there's another video directly below this one on bright space that will be concerned with issues of pH. So please watch both, and any questions, as I said, please do write to me so I can help you work them out. Thanks for watching.